if you listen to a church bell, it always has this sort of a wah 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 sound to it. Why doesn't it just slowly get quieter? That's what this video is about. But first I'll put this piece of coat hanger wire in a vise and pluck it. And you'll notice the vibrations seem to increase and decrease in strength over time as well. Why? The key here is to look at it from the end, and you'll notice that the vibrations never actually die out. In fact, they're always about the same strength. It's just they change direction and they change from straight line to circular. So if I'm looking at it from just one angle, sometimes it's vibrating like this, where seeing it from here it doesn't appear to vibrate, and sometimes it's vibrating like this, where it looks like it's vibrating a lot. Alright, next experiment. I've set up a simple pendulum here, and the period of the swing of the pendulum is dependent on the length of the string. But the way I have it hooked up, swinging this way, it's pivoting up here, whereas if I swing it this way, it's actually pivoting here because the strings are tied in a Y like this. What we're actually seeing is a pendulum swing that's going this way, plus a pendulum swing that's going this way, but they're going at different frequencies. And if we look at an angle, like for instance from this way, then we see the sum of those, which sometimes they're in phase and they'll be strong, and sometimes they're completely out of phase and they'll cancel each other. And getting back to our coat hanger wire, same thing is happening here. The frequency of oscillation this way is different from the frequency of oscillation this way. And if I pluck this wire exactly horizontal or exactly vertical, it won't make these patterns because it's only been excited in one mode of its oscillation at one frequency. I don't have a bell to demonstrate, but bowls will work as bells quite nicely too. We could think of a bowl or a bell sort of like a cylinder, and it can vibrate like this. Now this doesn't vibrate very well, but this is a bandsaw blade, and it will vibrate quite nicely. Now you may have noticed, as I was doing this, the points here and here don't actually move in and out at all. But I can actually just pluck it so that those points move the most, at which point the points here and here and here don't move in and out. Those are actually two separate modes of vibrations, and because of imperfections in a bowl or a bell, those are not necessarily at the same frequency. Now depending on where I strike the bell, I may or may not excite both modes of vibration equally, and depending on where the microphone is, I may or may not pick them up equally, so the amount of wow 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 will greatly vary with how and where I strike the bell. Now that's only covering the two major modes of vibration of a bell. Any physical object will have a lot of modes of vibration. For instance, a gong will have many modes of vibration. This isn't actually a gong, it's a stock pot. But a bell tends to have two principal, very strong modes of vibration. This piece of steel pipe is not a bell either, and you can tell that the two modes of vibrations are only slightly out of tune. For an experiment, I'll try to make some changes to it to make the two modes more out of tune than they are. I ground 4 flat spots on the sides corresponding to the nodes of one mode of vibration and the peaks of another, and that affects the tuning of them differently. And if I strike it between those two spots, it sounds both notes. But the coolest feature is, if I hit it to sound both notes and then spin it, you can hear the notes alternating.